Over the last week or so, I've not posted any new content, but I guess it's time for us to start back again, into posting new content. And so this week, we're going to talk about redox equilibria. Now, if you remember, over the last, couple of weeks, we've already talked about solubility product equilibria. We've already talked about pH or acid-base equilibria. And I remember when I was discussing the solubility product equilibria, I also mentioned, a little bit about complex formation equilibria, or what they call the complexometric equilibria. And this week, I'm gonna now focus on redox equilibria. And then later on, we're gonna talk about phase distribution equilibria. But this week again, we're gonna focus, on redox equilibrium. So the objective for this chapter, is for you to appreciate the relevance of redox equilibria for applications related especially to sensing. So my focus is going to be mainly on sensing, and I'm going to focus on a technique called potentiometry that is based on redox equilibria. All right. I think I'm also going to mention a little bit, about the other relevant application of redox equilibria, and that is things like the energy devices. If you look at most of the energy devices out there, the solar panels or the so-called the photovoltaic cells, they are based on electrochemistry or redox equilibria. Of course, there are other numerous physiological and environmental and toxicology, applications where redox equilibria is relevant. For example, I think I mentioned before, you've got, say, elements in different oxidation states. Say, chromium can have an oxidation state of 3 plus, but also it can have an oxidation state, of 6 plus. If you look at the toxicology levels of toxicities, of chromium 3 plus and chromium 6 plus is actually very different. Chromium 6 plus is more toxic than chromium 3 plus. And as such, electrochemical equilibria then is important when you're discussing, toxicology applications. And so sometimes it's important, to do what you call speciation, which is distinguishing different types of oxidation states, of different elements, because they've got different impacts as far as their toxicities, environmental, physiological toxicities are concerned. So hopefully you guys appreciate, the redox equilibria first, as an application for sensing, but also, for other types of applications as I have mentioned. It's important, for you to remember that each chemical entity, be it an element or a molecule, it has what we call electrochemical signature. And so we can use electrochemistry, for qualitative analysis, that is to differentiate different types of chemical entities, but also, of course, we can use it, for quantitation. Take a look, at the standard reduction potentials that you guys know about, for all different types of elements. And so we can say that different elements, they get oxidized at very, very specific, oxidation potentials, and they could also get reduced at very, very specific, reduction potentials. And you guys did this in Chem 101 and 102, about the standard reduction or oxidation potentials, for different elements. And that's what I'm saying, that every element or every molecule has got a very specific electrochemical signature, and as such you can use it for qualitative analysis. So for those of you in biology or interested in biological applications, I implore on you possibly to consider, and read on your own redox biology, which is another vast field, where electrochemistry or redox equilibria is very, very, very relevant. And so if I would say, among all the different types of equilibrias, that we've talked about, I would say in the environment, in the physiological applications, maybe redox and pH are the most relevant, of those chemical equilibrias. And as such, I'd like you to pay close attention to the relevance of redox equilibrium. So what do I mean by redox equilibrium? Redox essentially means re is for reduction, and redox, is for reduction, and OX, is for oxidation. All right. So essentially, we are referring to chemical reactions, that undergo reduction, which is an acceptance of electron, or undergo oxidation, which is a donation of an electron. When something donates an electron, for example, you've got a metal, and then it donates, an electron, you can see its oxidation, actually oxidation state increases, so that is oxidation. And of course, the reverse, is gonna be reduction. All right, so redox equilibria refers to these kinds of reactions that undergo reduction and oxidation. Now, you're gonna see that we'll be measuring, voltages, because anytime you've got, this transfer of electrons, you've got, voltage that is induced. And sometimes we call voltage as electric potential. We call it as voltage. Now, you can generate a voltage, and this is important. You can generate a voltage anytime you've got a charge separation. So anytime I've got polarization of a molecule, then I can generate, a potential difference or a voltage. I'll give you an example. Now, all of us have been facing major problems in the lab when we are doing weighing, because the analytical balances, keep fluctuating. And I keep telling you, chances are is because you're using the latex gloves, and the latex gloves induce a lot of static electricity. How do you induce static electricity or voltage? It is because of what you are calling the charge separation. Anytime I've got two dissimilar surfaces. In this case, it will be your glove and probably, the analytical balance or the beaker. I've got two dissimilar surfaces. Chances are I'm gonna have a charge separation that is induced because of those two different surfaces that have got different conductivities, and as such, they induce static electricity. When that happens, you can actually measure a voltage. Take an example, also, of our bodies as well. We are comprised, of layers of different membranes. And so each membrane, has got a certain voltage, because of it's a layer of different types of membranes. And so our bodies as well, have got a lot of potentials that are related to, different membranes, different tissues, you've got veins and so on. And again, all that induce an aspect, of charge separation as the ions, migrate, between different membranes in our bodies. And so you can see, again, electrochemistry or redox equilibria becomes very relevant, as far as, migration of the ions or metabolites in our bodies. So the basic function of redox equilibria, is an electrochemical cell. And so I'd like you guys to be reminded, of how an electrochemical cell works. I think all of us know an electrochemical cell typically comprises, of two half cells. And the two half cells, are conjoined, by, in the outer circuit, they are conjoined, by wires, of course, a conductive element, a conductive wire. And the inner circuit, is conjoined, by what you refer to as a salt bridge. And a salt bridge, it's just really a membrane, that can help in the transfer of the ions, between the two beakers or between the two half cells. And so the inner circuit, transfers the ions across the salt bridge. And by the way, the salt bridge can simply be a piece of paper, all right, where ions, can migrate between the two solutions. But also the salt bridge, sometimes people make it using a gel such as agar, and again, it's a semi-permeable membrane. Essentially, that's what it is, a semi-permeable membrane where ions can transfer between the two reactions, that are in the half cells. In the outer membrane, on the other hand, what you really have is the transfer of the electrons that would be resulting, from oxidation. Assume you've got anode in this case, cadmium undergoes oxidation to give you two electrons, that can be transferred through a wire, through an outer circuit, and then they come here to the silver. The silver accepts those electrons to make a silver wire, or to make, a coating of silver. And so that is really what an electrochemical cell, the two half cells, where the outer circuit, is giving you the migration of the electrons. And of course, that's electricity, meaning I can measure it using a voltmeter, or even using an amperometer, an ammeter, to measure amperes, and so on. I hope that's clear. In terms of the notation, we often use, these kind of two strokes to divide, the two half cells. Okay? So meaning this side is one half cell, the anode, and the other side, is the other half cell, the cathode. Now remember, we sometimes call this, a galvanic cell, meaning it's got these two components, these two half cells, and electrons are migrating, from the cathode, to the anode. So to measure the E of the cell, okay, the E of the cell, would be you take the half cell on the right hand side, meaning that guy, we call it an anode, all right? The half cell on the right hand side is called an anode. And then you subtract it, from the E, or the voltage, associated, with the left hand side, which is in this case, the cathode. Okay, and essentially when you do that, you're gonna measure the E of the cell, that's associated, with that reaction, that is taking place. And essentially, that is the basis, of a potentiometric sensor, meaning, in the cathode, I've got an unknown, and in the anode, I've got, what is known, or what you refer to as a reference electrode. So this one, the potential is known, and this one, the potential is unknown. And then I can now measure the E of the cell, which is going to be equals to the potential that is fluctuating, that is unknown. And as such, I can use, these kinds of electrochemical or potentiometric probes for detection. All right. So in this case, remember, in potentiometry, then we are actually measuring the voltage. We are measuring the voltage. In potentiometry, we are measuring the voltage associated with the redox reaction. And so you can use, these kinds of probes, for applications, such as determining even the end point, of a titration. Remember, for example, what we did before, when we were titrating, chloride, using silver, and we called it a gentimetric. We called it a gentimetric titration. So this is the analyte, and we are titrating the analyte using silver, and we call it a gentimetric titration. And we said the end point can be determined using color indicators, but also you can actually use you can actually use a chemical probe, that can measure silver, so silver chemical probe can be used actually for redox titrations, such as that. So in potentiometry, the voltages, that you get, of course, that is the E of the cell, and E, that one is the standard reduction potential, the standard reduction potential. Those are the voltage at standard conditions. Again, remember, those are constant, and I showed you earlier in the very first slide. And so you can actually measure, the voltages as a function of concentration using this relationship called the Nast equation. Of course, ourselves as analytical chemists, we are interested in concentration. Now, the instrument is giving us the voltage. What's the relationship between the two? The relationship between the two is based on these Nast equations. So the voltage that you get is proportional, to the concentration that you are looking for based on the Nast equation. Now, remember the RT and the F, the Faraday's constant, all those are constants. And when you calculate them, you're going to see the result in a constant, which is 59.196. So this one is results from the R, which is 8.314. Temperature at 25 degrees is 298 degrees Kelvin. And then the Faraday's constant, is that. And when you calculate it, you're going to see is equals to 59.16. And N refers to the number of electrons that are transferred, between the anode, where the oxidation is happening, and the cathode. Okay. And so essentially you can see I've got a reaction like this that is taking place, the redox reaction. And when I substitute, my products, the Q, the reaction quotient, the products divided by the reactants, you can see now this is the full Nast equation that relates my potential from the potentiometer and my Q, or the components of Q, the reaction quotient. Okay. You can see again, this is the variation of this, where this is the reduced species, divided by the reactants, which are the oxidized species. Now, remember, the Nast equation, can also give you the redox equilibrium constant, the K, redox. It can give you that. And again, based on the Nast equation, I think you've already seen this reaction. If we wait for the battery, the galvanic cell, to actually die, at that point, we say the reaction is at an equilibrium. Because you are getting, the same electrons, being generated during the oxidation, being consumed. And so I'm not getting any electricity being generated. And at that point, the reaction is at an equilibrium. And so the E is equals to 0. The battery is dead. And at that point, the Q, the reaction quotient, is equals to the K. And that's how people actually determine the equilibrium constant, of different types of reactions. You put them in a galvanic cell, wait for equilibrium to take place, measure the E of the cell at that point, which is equals to 0. And then what you'll be getting would be the standard reduction potential, which relates, to the K equilibrium constant. So I've just mentioned, for potentiometry to work, ideally what you want is, one of the half cell on the left hand side, this guy, which we called an anode, all right? And then this guy, we called it a cathode, okay? Ideally, we don't want both of them to be fluctuating. So often we would fix this, so that the only thing that is fluctuating, is what is on the left hand side, okay? And as such, we can get the E of the cell being equals to the E on the right hand side minus, the E on the left hand side. And the E of the left hand side, is actually, this one is called a reference electrode. And it's called a reference electrode, because the potential here is known. It's actually fixed. All right? And so the only potential that is changing is the right-hand side, which is what you would call the sensor. Sometimes they call it the indicator electrode. The right-hand side is what is changing, okay? So there are different types of reference electrodes out there. Now, you have the silver chloride reference electrode, and like I'm saying, the reference electrode, the voltage is known because the solutions concentrations are very, very well known, okay? And so in this case, actually, they make it, just by taking a silver wire, and then you bleach it using chlorine, you get silver chloride, and then you put it in a tube containing HCl, so that you can get this kind of a reaction, taking place. And the concentration of the HCl should be known. I think it's around 2.5 molar. And the potential is known. So that one is not changing. So this one is the most commonly used reference electrode. So that is the anode. Another common used reference electrode, is a so-called saturated calomel electrode. And it's very, very similar to the silver chloride. So the only difference is we replace the silver, with the mercury. And everything else remains the same. And the potential is known because it's 0.241. It's fixed potential. The last type of reference electrode is a so-called saturated or standard hydrogen electrode. And in this case, we just have a platinum wire. We replace the silver with a platinum wire. And then we fill the tube, with HCl. And we do electrolysis, so that we generate, hydrogen. And we have the potential fixed at 0.00 volts. And this one, by the way, it's arbitrary. It's just an arbitrary fixing, 0.00 volts, okay? But the most common reference electrode, is a silver chloride, because saturated calomel electrode, as you can see, it's made of mercury, and mercury is toxic, and so it's no longer very, very common. All right, and it's very, very easy actually to make these kinds of electrodes, and we make them in the lab all the time. My research group doesn't buy, we just make them ourselves. So that is potentiometry, and potentiometry, it's only one type, of electrochemistry technique. And so in the next lecture, I'm gonna talk to you about the different types of electrochemical techniques, with potentiometry just being one of them, okay? So potentiometry is just one of those techniques, but there are so many other electroanalytical techniques.